Auch die Universität Swansea.
Right, yeah. Yes, I would like to continue the theme of Monica's talk, program extraction. And this time I would like to talk about applications in computable analysis. So if we think of computable analysis, of course, everything started with Turing. His paper in 1936 about uncomputable numbers and applications to the Entscheidungsproblem. And there he already defined what a computable real number is, and also gave a sketch what a computable function on the real numbers is. And he defined it via Gödel numbers of computable real numbers. And I think using the Kreisler-Komp-Schönfeld theorem that one can show that his definition is actually the right one. Corresponds to the now established notion of a computable function on the real numbers, on exact real numbers, not approximations of it. Okay. Right, and I want to talk about a co-inductive approach to exact real number computation and how this can be used to extract quite nice programs from proofs you do in constructive analysis. Okay, so what is co-induction? So what's the really good thing here in this institute is that the talks are recorded, so I could look around what people have said about in previous talks, and Anton Setzer gave a talk where he explained, here he is, co-induction. And it's also good to hear what people say about you when you hear the other talks. So he made some statements about what I did, and I will comment on this later. So co-induction is, I think, quite a confusing topic. Nobody knows really what it is, or many people are not sure what it is. And you will get different answers depending on whom you ask what co-induction is. I'd like to just to list a few answers. In type theory, roughly, let's say the vulgar form of co-induction is induction without base case. So you have you prove A0, like induction goes as follows. From AN you deduce AN plus 1, and then you conclude that whenever n is a natural number, then A of n holds. So roughly. This is what induction is. And then co-induction would be just say we don't need a base case. This is of course quite wrong, but that's what people say. And is this still a valid principle? Well, if you have the base case, then you can get for any concrete number a proof by just doing always the step, and then eventually you will get down to 0, and then you need the base case to compute it, to complete that proof. And if you don't have this base case, you have to go on forever. You never are able to complete this proof. So in other words, what this really means is that the view in type theory of co-induction is that you are allowed to have infinite or even non-well-founded proof trees. And of course, you cannot use arbitrary such chains. There is a condition, namely that this step here must be guarded. And also the other, of course, important thing is here we justify this by the fact that the natural numbers are inductively defined. So this recursion will stop. Whereas here in the co-induction, this can be anything, and this has to be co-inductively defined and by some constructors, and then the condition is that the step proof here has to end with a constructor. That's a very rough explanation. And but it's not so easy to see that these proofs are in a logical way sound. They are rather recursive definitions of infinite proof figures. And whether they are not or not, they can be considered as a proof is another matter. And I won't go into this in detail. And Anton has said something about this in his talk. You could also ask other people, for example, in process algebra, then they would say, well, co-induction means that two processes or streams or labeled transition systems are equal when they are bisimilar. So this is based on the notion of bisimilarity. And you could ask people in category theory, they would say this is the universal property of final coalgebras. Universal property of final coalgebras. And finally, if you ask me, for example, or a set theorist, or somebody in lattice theory, you would say this is just the proof principle associated with greatest fixed point of monotone operators. So greatest fixed point of monotone operator. Okay? Just have to keep this alive for the demo. What do I mean by that? And this is actually the notion of coinduction we will use. And I try to, during the examples I will develop, I try to explain how this is related to the others and maybe shed some light on these other notions of coinduction. So what do I mean by this? I explain it not in principle, not in general, but always by means of examples. So, and the example will be from real numbers. So let's consider the following operator, phi, which operates on the power set of the real numbers. Okay, and is defined as follows. Phi of any set of real numbers is the set of all x, or let's call them y, such that y is in the interval I. I will always make use of this interval I, which is -1 to 1. So the real interval from -1 to 1, that's where we're actually working it. And it must be an I, and there must exist a signed digit. So what are the signed digits? Are just the numbers -1, 0, and 1. And there must exist a y, an x in x, such that y is the average of y, yes, is the average of x and d. I will write for this expression, which will occur quite often later, the average of x with d. So I write this as an average and d as a subscript. It's quite useful. Okay, so this is an operator. It assigns to every set of real numbers another set of real numbers. And what are the real numbers? Here I assume we are in classical mathematics. The real numbers are the real numbers with plus and times, and we use only the first order theory of it. We don't expect any constructive representation of the reals. It's just an abstract first order structure for us. Okay, and then we look at the largest fixed point of it. So we call this C0 is the largest fixed point of phi. So the largest fixed point of this operator phi. And then one can show that this set is quite interesting. One can show that an element x is in C0 if and only if there exists an infinite stream of signed digits. So A, let's say D0, D1, D2, an infinite stream of signed digits, such that this x can be written as the sum of all the di times 2 minus I plus 1. Okay? Of course, we know that this is exactly, classically, this is exactly that x is in this interval. So it's just this interval. But this proof is constructive. And moreover, I wrote this, I should have looked into my notes. What's more interesting is we do a realizability interpretation of our first order logic, and also we can interpret these co-inductive predicates, and then we can say such a stream A realizes this, and it's if and only if this holds. Yeah, that's what I wanted to say. Actually. And in that case, it's also true. It's also true that this holds. Then, yeah. Okay. So this true classically, if and only if this holds. But in a realizability interpretation, which is what is interesting for our project of program extraction, we say a realizer of such a predicate of this fact is an infinite sequence of signed digit that gives us this x. So this is an infinite signed digit representation of this number x. Okay? So please ignore this for a moment. So A is this signed digit stream. Okay, so what is this good for? Well, we can now prove theorems. For example, we can show if x is in Z0 and if y is in Z0, then anything that's continuous function is again in, so for example, the average of x and y is in Z0, and also the product of the two is in Z0. And when we have done this theorem, we are not interested so much in the truth of that theorem, but in the constructive proof of it. And in the program we get by extracting a program from the proof. And what would this program do? It would take a realizer of this fact and a realizer of that fact, which is a stream representing x and a stream representing y, and produce a realizer of that fact. So it produces a stream that has this as sum. So I hope this example shows that we get meaningful computational content about statements about real numbers, even if the real numbers themselves are given abstractly. So we don't compute with these real numbers x because we don't have a representation for them. But from this proof, we get a theorem that works, we get a program that works on the representations. And this program, this proof will be done by co-induction, which is this principle I didn't explain because I was rushing. So the principle of co-induction is, of course, if you have any property that is a prefix point of phi, then this p is contained in the largest fixed point of phi. So this is the principle of co-induction, which expresses that this is the largest set that has this property if you replace p by this thing. Yeah? And this is a simple rule, and you can use this to give a proof of that. So what you get for free from the program is the data structure representing real numbers. You get for free a principle of co-recursion, which comes out from the realizability interpretation, which I don't explain to you, but it's done once and for all. So you get the data structures and the program and the correctness proof. And the proofs we are doing, from which we are extracting the programs, are ordinary proofs that just use this extra rule. They are finite proofs. There's nothing infinite. We don't have infinite proofs, and we don't have to watch for a certain guardedness condition. So for my feeling, I mean, other people might have a different opinion. I feel safer here. I'm in the realm of first order logic, and I have no funny infinitary proofs and guardedness conditions around, and still get meaningful programs. Right. The next example I would like to give you to increase this index 0 to 1. Now let's look at real functions instead of real numbers. I want to give a co-inductive definition of uniformly continuous functions. First we start with an operator phi. It's a different one from that one. And this has two arguments. So it works on the functions from I to I times power set of functions from I to I to the power set of functions from I to I. So it takes two sets of functions and produces a set of function. And how is it defined? Fairly simple. So phi of f and g is the set of all functions f. Let's call them, I think it's, yeah, let's call them g. Of course, they must always be in I. I don't write this here, such that one of the two conditions holds. So either there exists an f in f such that, and there exists a signed digit such that this g can be written as average d, this average function here, composed with f, or else the other condition is for all signed digits, for all three signed digits, we have that if we precompose this g, with average d, then we are in G. Okay. Okay, it's just a definition, but I think in a minute you will understand what it means. But it's an explicit definition, nothing complicated here. And now we take, of course, largest and least fixed point, which makes it interesting. So C1 is now defined as the largest fixed point of the operator that takes f as input, and as output it computes the least fixed point of lambda g phi fg. Okay? This is C1. So C1 is a set of real functions. And so here we have a least fixed point and a largest fixed point nested into each other. So this least fixed point is parameterized by f. And why can we form this largest fixed point? Because still this phi is positive and therefore monotone in both arguments. And if you take a mu of the g, it still is monotone in f. So we are allowed to take the largest fixed point here. Yeah, so this mu is itself a monotone operator if you want a higher type. Okay? Now what is the rationale of this definition? Well, the idea is that the realizers of these functions, so I tell you what is a realizer. A realizer will be a tree, a realizer of the fact that some function f satisfies C1. Will be a tree that describes when this function reads or produces digits viewed as a stream transformer. View f as a function that takes a stream of digits, the input number, and produces the output number as a stream of digits. Then this f will sometimes read incoming digits, and depending on what it reads, it will produce some out digits. And the tree is described here. Namely, this function may read digits, and when it can read anything. It must be prepared to read any of the three digits for any. And reading means precomposing it with this average function. So believe me that this is what it means. And then it can loop to G and read again, but only finitely often, because this is the least fixed point here. And after finitely many readings, it must be prepared to output a digit. And this is what this says, because this means G is split into an F and an average D, this is the output digit, and this here you loop to the outer loop, the mu, which means you read finitely many digits, you output a digit, and you repeat this infinitely often. So that's the rough rationale of it. Yeah? So this T will be a tree. And then you can prove theorems, but this tree comes automatically out. So all the data structures that are realizing certain statements are automatically generated. We don't have to create this by hand, these data structures. And one can prove in theorems like composing. You can compose these functions. So if C1F holds and C1G holds, then C1F composed with G holds. So you can compose, and one can prove another theorem that says C1F holds if and only if F is uniformly continuous. So it's really a natural definition, but I don't go into this theorem now. So this will compose trees. You get a tree as two trees as input, get a composed tree as output. And there's another theorem that says you can interpret these trees as stream transformers. So if C1F holds and C0 of X holds, which is our first definition, then C0 of F of X holds. It's actually a special case of that one, because you can generalize this to n-array functions, and then this would be just function with no arguments. So this is unary function, therefore 1. So this means, given a tree and a stream, you get the output stream. Okay, now you can, all this has been implemented, and you can run it and try to implement certain functions. For example, you can prove another theorem that says define a quadratic polynomial with rational coefficients. For example, f, a, b, c, where a and b and c are rational numbers, to be ax squared plus bx plus c. So it's the family of all quadratic functions with of one argument with rational coefficients. And then you can prove if actually this function is well behaved. So if it maps I to I, because it's not necessarily the case, so this interval is mapped to itself by this function, then actually C1 of F holds. Okay. And what is the extracted program of this? It's a function that takes three rational numbers as input and produces the corresponding tree that implements this function A, this quadratic polynomial. Okay. It's just one application. So we get now implementation of quadratic functions, and now we can try this out whether it actually works in a interesting way. So could I have the screen, please? Thank you. Right. So, okay. I have prepared several demos, but probably I will only do this one demo with this family of polynomials. And plugging helps the quality of the presentation. I think it works just like that. It did last time. Yeah. Okay, here we have the implementation running. Everything is set up, and I produced a demo version of it. It's called main xk. I will just explain you what it means. I don't look at arbitrary such functions, but a special family of them, namely the so-called logistic maps. So if we have here the square, so minus 1, 1, I look at this function here, the special case of the logistic map. Yeah. So it's f of x is minus 2x squared plus 1. Yeah. That's the function I'm looking at. And then I iterate that to make it a bit harder. What happens when I iterate this n times? Fn has 2 to the n oscillations. So it's quite a nasty function to compute. And I will compute iterations of this function at the value 1/3. And I compare the exact result, which are computed using this method, with 16-bit fixed precision arithmetic. And I can vary these numbers. Okay. Let's start with 5 iterations. And I also do the exact rational thing, because this is a rational problem. If the inputs are rational, the output will be rational. Actually, there's no irrationality going on. So here's the exact value as a quotient, And here is this quotient written as a decimal, just with a number of digits. So we know this is correct here. And we know this is correct because we have extracted it. And this is done by 16 precision argument. And it's already getting a bit wrong here. If you go up to 50 iterations, I think we are already way beyond what this thing can do. Yeah, I don't want to do something else, sorry. Let's do 10 iterations. You see, this is the exact result. It gets twice as large every time you increase the iteration. So this shows actually that the biggest problem is the rational numbers. So the problem in exact real arithmetic is not that the computer reals are too imprecise, but the rationals are too precise. So they get really big, so you can't do this for a long time. So 15 iterations. This is the exact quotient you get. So I switch it off after 16, then I forget about the rational approach because it doesn't work. So here we only have our signed digit approach, and here we have the precision approach, and here we see it's getting already wrong. 60 iterations. Here it's quite wrong. So we can start again and maybe do a little bit of better precision. And then it's the 60 iterations. It's still quite right, but now if we do 100 iterations, it's still not too bad, but if you do 150, then it's completely unrelated to the correct result. Yeah? And now we can still get higher precision if we want. We can do 64 or even higher. But yeah, so we can do 64. But the question is how large do we have to make the precision to get the right result? So here you see this is quite good, but it's again getting quite wrong. So we wouldn't even know how good the thing is if we hadn't had the exact result. So the solution of what people usually answer, well, I just increase the precision, doesn't help. You need an analysis. What is enough precision? And so this implementation is not so bad, and it extracts the correct result. So I'm finished, yeah, or nearly. One thing I wanted to tell you more is that I cheated here a little bit. Namely, I trained my computer while Monica was speaking. I let it run. And why does it help? Because the data structure where we're storing numbers are trees. And trees are lazy data structure. They are computed. And once you computed them, they are kept in the memory. So you can reuse previous computations. So this remembering, this memorization is done automatically in a lazy language. Well, it has to be lazy because these trees are non-well founded. So if I now start again and reload it, it would be much faster. Only after a while it remembers all these computations and gets better. So in certain cases there's quite a big speed up by this automatic memorization, and it's, as far as I know, the first representation of real functions that has this automatic memorization built in, because the data structure is a tree, finally branching tree, and not a closure or something else, what you normally would represent a function like. Yeah, I think I have to stop. Thank you very much for your attention.
Question or comment? No? Yes.
These trees can get very large, can't they?
Yeah. Yeah, they're infinite.
Yeah, I mean,
anyway,
for
but
storing.
the point is that you compute only a finite bit of it, and you convert a little more on demand. Yeah, you mean problems with the memory? Yeah, of course, but memory is cheap. I mean, it can be the wrong method, but it can be the right one. It depends on the applications. Yeah. I must now show this tree. Here is a tree, for example. That's how they look like. Yeah. Of course, it goes on forever. This is the tree for that function, an initial segment. It says, okay, I put out the big surpluses, say when When I give out a digit, and the branching means I read, and whatever I read, I have to go into the corresponding branch. That's how the trees look like. But they're infinite, but a lazy language like Haskell, where we're running in this in Haskell, only computes on demand finite bits of that tree. And what it has computed, it remembers. Okay.
Okay, I think we should stop there. Thanks again.
Okay.